if we have a high value at, let's take 0.3 here. If we have a high value here at 0.3, that tells me something about the spectrum of my input signal. Yes? Okay. My question is, this 0.3, to what frequency does that correspond? Okay. It tells me something about the spectrum of the signal. At what frequency does that tell me something about the signal? Like, what is the frequency corresponding to this 0.3? To figure it out, we need to go back to our DFT derivation slide. Okay, so the DFT, you had some continuous signal that you then sampled, and then you windowed that sampled signal, and that's what you got here at this point. Okay, it's a windowed signal. There's zeros here, zeros here. Because it's a windowed signal, a little bit of a wiggle got on our frequency domain stuff. And then what we did was we periodically extend this thing. We repeat it periodically, which corresponds to sampling in the frequency domain. Tunk, 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 tunk. And the result of that is basically two discrete signals for which we can keep the amplitudes. And that's really what the DFT does. It tells me that like the strength here is related to the strengths here through the DFT. So now this is the question that we're asking. This 0.3 here, what frequency, what continuous frequency does that correspond to? So obviously this signal in some way has some content at that 0.3. What is the frequency at this point, 0.3? Instead of talking about 0.3, we can ask, like, for an arbitrary point here, point k, the frequency at point k. What is that? But we can take 0.3 here as an example and say, what's the frequency at that point? Okay, can you guys tell me? 3 times the sampling frequency. No? Okay, but I like some of the words that you said. So you've said sampling frequency. Okay, that's good. So it's going to be some factor of the sampling frequency. Again, on this picture, where is the sampling frequency? I'll use my pointer and then you tell me stop when it's close to the sampling frequency. Okay, tell me stop, stop, stop. Okay, yes. Congrats. Okay, so the sampling frequency sits here. That is actually Fs. Fs is 1 over T, and that is my sampling frequency. I'll ask again, that's the sampling frequency. Like if I had to draw a little axis here at the bottom here, and I call that axis F, and I ask you what happens at F3, what is that frequency? So the frequency here is 0, the frequency there is F3. How would you express F3 as something with Fs? I'll help you a little bit. So on this little axis here, Fs is here, okay? So on this thing, it's here, which is NF. So here on this little plot, it's there. This is Fs, okay? And now F3 is just some fraction of Fs. What is that fraction? 3 over capital N, spot on. Do you guys see? So there's capital N points. Basically, we took the frequency axis between 0 and Fs. We divided it into capital N like snippets, and the third one is just a third of the way there. Okay, so let's just draw that out on this slide, and now we won't talk about the third point. We'll actually talk about the kth point. So we have a little axis here, and that axis we call F. This is 0, and Fs corresponds to this nth point. And this third point here is then like a third of the way, well, 3 over n of the way. So if we think about the sampling frequency at this kth point, it's just some fraction of Fs, and that fraction is basically k over n. The DFT is wonderful and makes you like happy on the inside because you can calculate it on a computer, but when you call the function on the computer, what you're going to get out is a list of numbers. And it's not going to tell you which frequency corresponds to which number. It's just going to give you a capital H0, a capital H1, a capital H2, capital H3, capital H4, and so on. And then you're going to have to figure out, okay, well, capital H5 is very high. What frequency is that? And this is what this relationship tells us. There's another axis that I like, the DFT axis, which doesn't have like sampling frequency in it. What's that axis called? Can you remember? It's f omega. Okay, and f omega you just divide by fs everywhere. Okay, and that's the cool thing, because then your sampling frequency is always, what's the value here in f omega? 1, yes. Okay, so this point here is 3 over n times fs. What is the corresponding point here on my f omega axis? 3 over n, okay? Or in general, so this is 3 over n. So in general, if I have my capital H K sample, then on this axis that will land at k over n. Okay, and it's a little bit, so let me just write this out. So f omega in terms of k, that will just be k over n. Everyone happy with where, like if you now calculate the DFT, which you will do in NumPy by just calling np.fft.fft, that will give you a list of numbers, and then you should be able to figure out, well, the 7th number, which frequency does that correspond to? And that's just k over n, 7 over n, if it's the 7th number. Happy on the inside? Okay.